Hi, everyone. Today, I'm going to talk about when is there a linear representer theorem. So this paper majorly talks about the necessary and sufficient conditions for linear representer theorem to hold for a very particular class of regularization problem. And so the original paper, the title is When is there a representer theorem, vector versus matrix regularizer. But in this presentation, I will focus only on the first half of the paper. So, and the first half of the paper only talks about learning a vector of parameters. In the second half of the paper, they extend these necessary and sufficient conditions to learning a matrix of parameters. But a vector of parameter is like really very relevant to economics research because we largely focus on linear models and we run a lot of linear regressions. So hopefully, after presenting on this paper, I can extend some of the ideas in this paper to my economics research and expand the methodologies that we as economists use. So the presentation is set up like this. I will go through the problem setup. In this problem setup, I will first define the particular class of regularization problem that we are going to solve. Sorry, not we are going to solve, but where the linear representer theorem hold. And then I will define an associated interpolation problem, because it turns out that proving for necessary and sufficient conditions for the regularization problem is would be much easier. To do that, it's much easier if we just do it, if we just establish equivalency between the representer theorem holding for these two types of problem, and then prove the necessary and sufficient conditions for the interpolation problem. In the second part of the presentation, I will establish that equivalency, the equivalency of linear representer theorem holding for either the regularization problem or for the interpolation problem. It turns out that the theorem holding for these two types of problem, they imply each other. So we can sort of see them as being equivalent. In the last part of the presentation, I will show the necessary and sufficient conditions for the linear representer theorem to hold for interpolation problem. So in that part of the presentation, I will define what is admissible. I will give a geometric interpretation for the necessary and sufficient conditions. And eventually, I will show the equivalence of the conventional sufficient conditions is actually equivalent to the necessary and sufficient conditions to, or the geometric interpretation of the necessary and sufficient conditions for admissible. Okay, so now let's set up the problem. So here we are solving a regularization problem. Notice that it's slightly different from what we learned in class. So here I define the inner product as the standard way, which is one vector multiplying the other. And it's slightly different from what we learned in class, where the functional form is a little more restrictive. Here we specify the relationship between the learned vector, which is W, and X. So it's W transpose multiply X is what is the function that we specify. In class, I believe our input data can take on nonlinear transformation, right? Because so for example, our phi nu X is X to the power of nu divided by nu factorial. So that is a nonlinear transformation. And also the representer is also, I believe, a nonlinear transformation of X. So here, our functional form is more restrictive, but we allow for a more general arrow function. So this is the arrow function. In our class, we mostly study about square laws, right? From lecture notes set 1 all the way to set 6, we study about squared laws. It's only until the last set of lecture notes we learned about hinge laws, and also we briefly talk about logistic laws. So all these three types of losses, they also satisfy the necessary and sufficient conditions that we are going to present, that I'm going to present later on. So here, the linear representer theorem applies to this type of problem where the solution takes on the solution W hat is a linear combination of input data. Okay, so now I define a associated interpolation problem. So the associated interpolation problem is essentially we let gamma converge to 0 or a infinitesimally small positive number. Yeah, so we want to minimize the penalty, but we enforce that the inner product of the solution of this interpolation problem and the data and our input data is equal to the solution for the regularization problem and the input data. So in the rest of the, so after I defined these two types of problems, in the next part of the presentation, I'm going to establish that when the linear representer theorem holding for one class of problem will imply the linear representer theorem also hold for another class of the problem, and the converse is also true. And then after that, I will show the necessary and sufficient conditions for the linear representer theorem to hold for the interpolation problem. So here, the lemma is saying that when both the regularization problem and the interpolation problem, they have solutions, then when we have the linear representer theorem holding for interpolation problem, then the linear representer theorem will also hold for regularization problem. So here's the proof. We start with a regularization problem with a solution W hat. This is true because we already hypothesized that both regularization problem and the associated interpolation problem have solutions. And then we defined the associated interpolation problem, which has the solution W tilde. So remember that for the interpolation problem, we enforce that the inner product of the solution and the input data is equal to the inner product of the solution for the regularization problem and the input data. So that means this equality must hold true, and when this equality holds true, the arrow function value also are equal to each other for these two types of problems. But by construction of the associated interpolation problem, we are minimizing this penalty term. So this penalty term for the interpolation problem is necessarily smaller or equal to the solution for the regularization problem, since their arrow function take on the same value. And the penalty term is smaller for the interpolation problem. Then the solution for the interpolation problem W tilde is necessarily also the solution for the regularization problem. Hence, the linear, since we already hypothesized that the W tilde, which is the solution for the interpolation problem, is a linear combination of the input data, then the linear representer theorem also applies to the regularization problem, because the linear representer theorem is essentially just saying that the solution is a linear combination of input data. Okay, now we have established one way of the relationship. We want to also establish the other way of the relationship. That is, when the linear representer theorem is true for regularization problem, we want to show that it's also true for interpolation problem. So we impose some additional constraint on the some additional conditions on the error function and the penalty function. And also we assume that there exists the V from the, I think this is the sample space. Then there exists a unique minimizer for this minimization problem, and the minimizer is not 0. So for this part of the proof, for this theorem, the proof, I'm not very confident about my understanding of the proof, but I did write a lot of my, I did detail my understanding on the paper. So I will upload the annotated paper. And you guys, if you guys are interested, you can read it and maybe you can discuss about it. Okay, so now I move on to the next part of the paper. So instead of giving you the proof for the theorem, I will show you some of the examples for the eligible functions, arrow functions that fulfills the conditions that we have shown in the previous theorem. So all the loss functions that we learned in class, which includes square loss, hinge loss, and logistic loss, all fulfill this the conditions that we impose on the arrow function. So when we use these three arrow functions, then and on top of having some other conditions on the penalty function, then these two when the linear representer theorem holds for one class, it will also hold for another class of problem. Okay. Now that we established the equivalency for linear representer theorem holding for both classes of problem, we go to proving or exploring the necessary and sufficient condition for the interpolation problem because it's easier to prove. Okay, so now we define a new interpolation problem. Now we are just replacing the inner product of the regularization problem solution and the input data. We replace that with the output data y. Okay, so now this is the interpolation problem that we want linear representer theorem to hold, and we define a term admissible. That is essentially it's just saying that when the penalty function omega is admissible, then given that the interpolation constraint is satisfiable, then linear representer theorem hold for this interpolation problem. And the linear representer theorem is stating that the solution of this problem is a linear combination of the input data. All right. So this theorem is the sufficient, essentially this part of the theorem is stating a sufficient condition, and it is well known for with regard to this particular regularization problem or interpolation problem that we are learning, that this is the sufficient condition for linear representer theorem to hold for the type of regularization and interpolation problem that we are talking about in this paper. And it's just saying that this function, this penalty function, is a non-decreasing function of the norm of W vector, which is the vector that we're going to learn from this problem. So to prove that, we essentially break the proof into two steps. The first step, we endow a geometric interpretation of admissible. And then in the second step, we establish equivalence between this, this geometric interpretation and the conditions that is stated in the previous theorem, which is this condition, all right? This condition. All right, so I'm not gonna go through this part of the proof because I don't have an understanding of the proof, but I do think I have a pretty good understanding of the first part of the proof. So I will go through that with you guys. So the geometric interpretation is really nice because if you draw it on a graph, it's as if we are drawing contours. And then we just want to say that the penalty function, when the input is a sum of two orthogonal vectors, then the penalty function necessarily take on a larger value than when the function only takes in one of the orthogonal vectors. If you don't understand what I just said, then you can look at this graph. I think this graph is a pretty nice illustration of this condition here. All right. So we want to prove this if and only if lemma. So we will prove one way first. So at first, I think here we assume this condition is true. Then we consider any W vector. We can consider arbitrary vector W hat. Then we can decompose W hat into two vectors. The first vector, W bar, is from the span of the input data. And P, which is the second vector, is from the orthogonal space to the vector space spanned by the input data. Then from the construction, from this decomposition, we know that W hat, the inner product of W hat and X is equal to W bar and X because P is orthogonal to the space spanned, the vector space spanned by X. Okay, so we also assume that this, right? When two vectors, they are orthogonal to each other, then when we sum them up and put that as the argument for the penalty function, then the penalty function takes on a larger value than omega W, where W is one of the orthogonal vectors. So this is necessarily also true for W bar and P because they are orthogonal to each other by construction here, right? So, okay, sorry. So because of that, we know the arrow function takes on the same value, whether it's W hat or W bar, but the penalty function for omega W bar is smaller than omega W hat, correct? So W bar, so whenever we find we have a arbitrary vector W hat, we know that the component of W hat that belongs to that is in the vector space spanned by the input data necessarily has a smaller objective function value. So W bar is necessarily the solution for the interpolation problem that we are talking about. So, and also W bar is within the span of the input data. So the linear representer theorem holds because this is essentially saying the linear representer theorem. So now we have established that when this condition is true, then the linear representer theorem holds. Now we want to show the opposite, which is when linear representer theorem holds, then this condition is necessarily true. So here we go. We again choose any vector W, where W is from the from H space, whereas the possible space that essentially is the sample space, I think. So we want to minimize this problem where we want to solve. So essentially, this is the interpolation problem, right? Where the interpolation problem, but now we only have one data point, and that one data point is W, and that is the one input data that we have. The output data here is the norm of W, which is also the input. The inner product of W and 2 itself. So since omega is admissible, we already assume that, then the linear representer theorem holds, and then we know that the solution for Z, which minimizes this problem, must lie in the span of W. And we know that this must be true, right, for the solution. So this must be true. This is true, then Z, since it lies in the vector, right? Essentially, it just lies. We already know the direction because it must be within the span of W. So the only point that this can be true is when Z is equal to W. And also we know that if we add an orthogonal vector to W, then W plus P, its inner product with W is also the norm of W, right? Because W and P are assumed to be orthogonal to each other. Okay, so since this is true, then when we let Z equals to W plus P, then this is true. So every single W plus P vector is also a possible candidate to the solution. But we know that our solution is z equals to w. So that means, and also we know that the arrow function must take on the same value. So the penalty function, which is omega w, must be smaller or equals to omega w plus p, correct? So now we have established that the geometric interpretation is the necessary and sufficient condition for admissible omega. Okay, so next up, we are supposed to show that this geometric interpretation is also equivalent to the conventional sufficient condition that we have for linear representative theorem to hold for the interpolation problem. But I don't really understand that part of the proof. So if anybody is interested in this idea, you can read the paper and maybe someday we can discuss about it. And I had a lot of fun taking this class. Thank you for watching this video.